In this video, we will discuss a few aspects of the Flash's powers, discussing what it takes to run on water, as well as the more fantastical elements of moving faster than light and time travel.
Firstly, you don't need to be moving fast to run on water. There is no minimum horizontal speed to stay on the surface. In fact, the only thing that matters is can you push against the water with enough force to support your weight. Force on an object moving through a fluid is proportional to the density of the fluid, the square of the velocity, the wetted area, which is basically the area of the object pushing against the fluid, and a parameter called coefficient of drag, which we'll talk more about later.
The most efficient way to generate sufficient force to keep yourself up would theoretically be to stand still and stamp your feet as fast as possible. However, according to research done on basilisk lizards, it would take approximately 15 times more power than a human can produce to support their own weight.
This would be no problem for the Flash, but if you want to move quickly over water, you need to be able to produce more force. In the show, Barry asks,
"How fast do I need to go to run on water?"
Approximately 650 miles an hour.
We've already determined there isn't really a minimum speed to run on water, but how much power would it take to run that fast? While drag is helping us run on water, it can also be a big problem if you want to move at speeds this high. We can figure out how much drag will be acting on the Flash by using some data from a real-life speedster, the only person to ever break the sound barrier without a vehicle, Felix Baumgartner. When he made his record-breaking jump, he reached speeds of 1.3 times faster than sound. Using the data from his flight, scientists were able to calculate the coefficient of drag of a person at high speeds.
Using this data, we can calculate the drag for someone running at 650 miles per hour. Felix was wearing a bulky pressure suit for his jump, meaning his wetted area was around 1 square meter. We can assume the Flash would be a little smaller, it's around 0.75 square meters. Using the density of air at sea level, this gives us a drag force of approximately 25 kilonewtons. Unlike most runners, the Flash needs to develop far more force to overcome drag than he does to support his weight. This would mean to run on water at 650 miles per hour, he would need to be producing around 480 times more power than a normal person is capable of.
This all can be understood using Newtonian physics, but in the comics, the Flash is said to run at multiple times the speed of light. This fantastic powers explanation relies on an omnipresent source of energy across the DC multiverse called the Speed Force. All his superpowers rely on faster than light travel from the Speed Force, so an interesting question is to ask, how realistic is this power?
Let's start with the basics of special relativity, which will help work out what happens when an object, like the Flash, travels at speeds beyond speed. Since the days of Isaac Newton, physicists thought space and time were separate and unchanging, like a set of axes on a graph. However, Albert Einstein showed us that they are intertwined and relative through his theory of special relativity.
He stated two things. The laws of physics are the same for all observers, no matter how fast they're moving, and the speed of light is always the same, 299,792 kilometers per second. This is for all observers and regardless of their motion.
These postulates laid the groundwork for understanding the relationship between space and time. Let's break down why these rules stop the Flash from travelling faster than light. As the Flash approaches the speed of light, time will slow down in his reference frame. This is called time dilation and occurs according to the Lorentz factor. This is explained in Flash number 123 when Barry Allen meets Jay Garrick and they experience time differently due to their speeds.
One might logically think that if the Flash was running near the speed of light, a small acceleration should push him over the edge. Otherwise, the conservation of energy will be broken. Let us test what happens when you try accelerating at relativistic speeds. Special relativity tells us the kinetic energy is given by this equation, but gamma is the same Lorentz factor as before.
To conserve energy, the mass of the Flash increases while velocity asymptotes at the speed of light. William Bertozzi provided experimental proof of this by accelerating electrons to super high speeds and measuring their kinetic energies. It may seem like all hope is lost with the Flash, as special relativity seems to rule out any way to travel faster than light. However, Einstein provides us with hope with his theory of general relativity.
General relativity is Einstein's theory of gravity. Rather than thinking of gravity as a force between two masses, Einstein explains it as the curvature of spacetime caused by the presence of mass and energy. Mass and energy warp the fabric of spacetime, and the motion of objects through this warped spacetime is what we perceive as gravity. This is mathematically described by Einstein's field equations.
So, when we talk about faster than light travel in general relativity, we're not talking about an object moving through space faster than light, but a manipulation of spacetime that allows it to happen. let us explore two potential solutions and why they can or cannot work.
One of the most famous solutions to Einstein's field equations that involves such warping is the wormhole, which might just allow for faster-than-light travel in a different way. In the Flash number 182, the Flash is said to use a speed vortex, which is described very similarly to wormholes.
A wormhole, also known as an Einstein-Rosen bridge, is a theoretical tunnel that connects two distant points in space-time. Instead of travelling through the normal space between these 2 points, a wormhole lets you take a shortcut through the folded fabric of space-time. Imagine it like folding a piece of paper so that two holes line up. You can move between the 2 points instantly, bypassing the vast distance between them.
For a wormhole to exist, the space-time must be curved in a very specific way that creates a tunnel-like structure. The simplest theoretical wormhole, the Schwarzschild wormhole, has the following form for the space-time interval.
However, there's a catch. These wormholes are theoretical. To keep a wormhole open and stable, we need something called exotic matter, material with negative energy density. This exotic matter would be required to prevent the wormhole from collapsing under the influence of gravity. Later in the video, we will explore the world of exotic matter and ask if this is possible or a simple theoretical dream.
Another potential solution offered by general relativity is the Alcubierre drive. Named after physicist Miguel Alcubierre, this idea is based on the premise that you don't need to move faster than light through space. Instead, you stretch and compress the space itself around you. This creates a warp bubble around the ship, in which the ship itself doesn't move faster than light inside the bubble.
While the object inside the bubble doesn't break the speed of light, the bubble itself can travel faster than light, since it's the fabric of space-time that's moving. This is the key equation that describes this warp bubble. In the Flash, Born to Run, Wally West describes the speed force as a current of energy, which is similar to a warp bubble from the Alcubierre drive. Like wormholes, the big issue with the Alcubierre drive is that it requires exotic matter. Let us explore exotic energy and see if this can allow the Flash to travel faster than light.
We have talked about how the non-existence of exotic matter may be the limiting factor for faster-than-light travel. So let us explore this magical substance. Exotic matter is a theoretical matter that has negative energy density, which means it would behave in the opposite way to regular matter. Regular matter gets pulled into gravitational fields, but exotic matter would have the opposite effects. It would repel instead of attract. In other words, it would have negative mass or negative energy.
Is there any evidence for exotic matter? Right now, there is none. In theory, exotic matter could be created through quantum fluctuations, where the vacuum of space itself fluctuates in energy. In certain quantum field theories, particles can briefly pop in and out of existence, and these fluctuations could, in theory, produce negative energy.
One place where we might observe something like exotic matter is in the Casimir effect. The Casimir effect happens when two closely spaced conductive plates create a force between them due to vacuum fluctuations. This isn't quite the same as exotic matter, but it does hint at the possibility of negative energy in very specific conditions. But until we can directly create and manipulate exotic matter, we can't say for sure that it exists.
Finally, one last shot to make exotic matter work is how Flash might be using tachyons. These are hypothetical particles that have imaginary mass, which allows them to travel faster than light without violating special relativity. In the comics, the speed force is said to be caused by the interactions with tachyon energy.
So could tachyons exist? According to the maths, they could, but there's no experimental evidence to back up their existence. They remain a theoretical concept within both special relativity and quantum field theory. In the world of comics, however, tachyons are a convenient tool to explain the Flash's amazing ability to break the speed of light.
So, after diving into both the theories of special and general relativity, what have we learned about the possibility of the Flash travelling faster than light? Let's break it down. Due to special relativity, nothing with mass, like the Flash, can exceed the speed of light, and time itself slows down due to time dilation. General relativity opens some fascinating possibilities, like in the Alcubierre drive, or wormholes, that a Flash could exploit. However, to keep a wormhole stable and open, you would need exotic matter with negative energy density. This is purely theoretical, and the energy requirement would be enormous.
So, could the Flash travel faster than light? The answer is, in theory, yes. If he could somehow find or create exotic matter to stabilise a wormhole, he could use it to bypass the light-speed barrier. But, in practice, there are some massive hurdles, from the existence of exotic particles, or the fact that we don't yet have the technology or understanding to manipulate space-time on that scale? It seems that this physics has already been discovered in the world of DC Comics.